Welcome, everybody. It's a pleasure to introduce today's speaker, Christiane Jablonowski from the University of Michigan. Christiane got her diploma in metrology, both in Germany, from Aachen University of Technology and the University of Bonn. Then moved over to do her PhD at the University of Michigan and joined NCAR as an ASP postdoc in 2004 and had a brief visit at GFDL and came back to Michigan afterwards and stayed ever since. Christiane has a very broad research interest, worked on many topics, including atmospheric dynamics, Great Lakes, weather research, machine learning, but is probably mostly known for her work on dynamical cores and atmospheric models, which is also a topic that she is talking about today. She worked on specifically grid refinement, surface scale mixing, and also developed simple atmospheric models and test cases for dynamical cores. And today, Christiane is talking about shedding light in hidden aspects of dynamical cores. So thank you for joining us, and the floor is yours.
Thank you for the nice introduction. So it's great to be back at NCAR. So as you heard, I was a postdoc here many, many years ago, and it's always a pleasure to come back. I'm also very active, for those who don't know me, on the CESM side, so in connection with CGD, and serve currently on the scientific steering committee for CESM. So I come to NCAR on a regular basis, especially now after COVID. It's good to be back and not to be remote. All right, I picked that topic, which is not the classical M-cubed topic, but I did pick it to raise awareness of the dynamical core issues that you might not be intrinsically familiar with, and I just want to give you some options. Yeah, I want to just open the black box. So often the dynamical core is considered a done deal. You know, you might hear from scientists or even agencies that all the problems we have in our GCMs or weather models are in physics. That's actually not necessarily true, and I want to just really give you some ideas what is possible or not possible, or where the issues lie in dynamical core research. And I'm very flexible, so if you have questions, please feel free to interrupt at any time. I also want to leave, of course, time at the very end. So I picked that title to really illustrate that things often get, pushed under or swept under the rug. Yeah, and here what I really mean is the dynamical core dissipation. And you will see that that word alone means 20 things. Yeah? So it's not just one mechanism. And I will touch upon a few. I of course, can't, in 45 minutes, I can't really present all the options to you. I just want to really raise awareness that this is a really complicated portfolio often of dissipation techniques that, in the end, keep the dynamical core stable. This is also work that where my student Owen Huge contributed to, and also, if I have time at the very end, I want to sneak in a couple of slides from Lou Wicker, who is at NOAA and SSL. And yeah, George.
Is that a picture of Bill Skammerock?
All righty, well, your choice. Your choice. And of course, I should also, as you say the name, I should highlight that, of course, M-cubed has experts in this area as well, Bill Skammerock, of course, or Joe Klemp, who have published in these areas. So yeah, this is, I guess, from a dynamical core viewpoint, yeah, this presentation. Alrighty. Let me see whether I can, oops. Oh, all right, do that. Oh, I think I'm frozen.
Is the laser pointer still going? Yes.
Yeah. Oh, I think I'm frozen here on my first page. Oh, let's see. Okay, all right, thanks. Okay, let me kind of jump in. Before I actually jump into the topic, I also thought I'd take that opportunity and advertise a workshop that we will organize next year. And this is actually the 5th workshop on physics dynamics coupling in weather and climate models. So this brings together kind of the weather and climate community and also the physics and dynamics community. So this will actually take place at the University of Exeter in the UK next summer in June. It's organized by Gemma Shipton. She's a professor there, but it's co-organized by many other people, including me. So maybe if you are interested in the topic, you see a little bit of that here in this presentation. Keep an eye open. The website isn't quite up yet, but this is kind of the date. At least you have that information. Also want to advertise, since I think this is a great opportunity, potentially two postdoc positions in my group. So if there are postdocs either online or in this audience, or postdocs that watch maybe later, I'm happy to talk to you about possibilities and opportunities. And one model configuration or model problem we are looking at is, here's the Great Lakes area. You kind of see the Great Lakes here. This is actually a satellite image of lake effect snowstorm. That is very frequent in our area, and we are here using the unified forecast system, basically the NOAA's weather prediction model, which is under development, convection resolving, or permitting, I should say, to kind of do a better job with the coupling of the Great Lakes. They are kind of, actually implemented or presented by a lake model called FECOM, but we are coupling basically a Great Lakes model and the forecast model. The hope is to have better weather predictions in our area for those weather situations. The other opportunity is on more technical aspects, dynamical core research, and also physics dynamics coupling. So again, if people are interested, please reach out to me. Okay, all right, so this is what I meant when I talk about dissipation. I mean 20 things, yeah, and this is an impossible slide. Normally I would not do that, yeah, so this is full of keywords and mechanisms, but I chose to do this to just give you that flavor, yeah? So you probably don't know half of this. Yeah? I just want to walk you through some options to have at least an idea what's out there and what I say when, there is basically, and this is true for all dynamical cores. All dynamical cores have some sort of dissipation, but not necessarily that. Yeah? So here's an example which is really complex from NOAA's finite volume cubed sphere dynamical core. That's called FE3, which is at the basis of the unified forecast system. It's actually also available here at NCAR as part of CESM. So if you get a fresh version of CESM, that would be available to you for experimentation. But what do we have? Well, we have, maybe I'll take my mouse here. We have explicitly added horizontal divergence damping. This is something you put on top of the equations of motion. There's also vorticity damping, and you see this is even a choosable order, so it can be more scale selective. Here are a couple of options. We have sponge layer diffusion. That could be Rayleigh friction, if you have heard about that. This is really just friction. Or it can be enhanced divergence damping or enhanced Laplacian diffusion. There's also, and this is again coming from the FE3 model, there is a Smagorinsky-like divergence damping. What that means, Smagorinsky means that the coefficient in front of divergence damping is kind of tailored to flow conditions, like the deformation. Then we have, in addition, we have a 2 delta X filter. This is now working in the vertical, actually. We have something called external mode damping. Again, if you haven't heard these words, that's fine. Yeah, I don't have time to explain everything, but just kind of hit home the theme that it is complicated. We have some implicit horizontal numerical diffusion, at least 5 options. And I'm highlighting actually also a couple of these keywords here in red, H-ort and N-ort, because I hit that home a little bit. So you see this again. We have also in the vertical, we have different diffusion. This comes via an interpolation method in this floating Lagrangian coordinate system. And then we have choices to make. For example, do we want the energy that gets lost due to friction, do we want to put it back into the dynamical core as heat? And this is called frictional heating. This could be done locally or globally. We are some fixers, or it can also be limited. So this is all a choice you make. And then we have, in addition, energy fixers, mass fixers, angular momentum fixers. So this is things we would like to conserve naturally, but often we don't, yeah, because of numerical issues. And so we can decide to do this artificially. That's kind of the fixer idea. And what I'm leaving out, and many other models have that, this would be called Laplacian diffusion or hyperdiffusion. That's available, for example, in many of the CSM dynamical cores and even in MPAS. And there could be also filters, Shapiro filter, for example, or 3D divergence damping, which is different than 2D divergence damping. So, okay, long story, short conclusion. It's complicated, yeah. So I'm focusing just on two, and this means I'm focusing a little bit here on the horizontal divergence damping and also on numerical diffusion, which is implicit diffusion. It's very hard to tune, or it can't even be tuned that well. Okay. Well, many years, 10 years ago or so, I got together with Dave Williamson, who was a senior scientist in CGD, and we decided that it's worth writing a book chapter on this. So if you now want to know all the glory details that I don't present, I encourage you to take a look at this. This came out of an event we called DCMIP. DCMIP stands for Dynamical Core Model Intercomparison Project. And this is something where we brought into NCAR the international community of dynamical core modelers back in 2008, 12, and 16, 3 times. We spent 2 weeks here at NCAR and were discussing all the dynamical core issues that might be there, not just the ones I show you. It was so rich that we decided to write a book, and I wrote a book chapter that's 113 pages about diffusion. So this is, and this is probably not all. You probably can even add more pages to that. So it is, if that is intriguing, I also would like to kind of point out there's another, this is now just a publication. We also published a little bit more here on the divergence damping a couple of years ago with Ricky Root, who's actually in the back, my former colleague here. Alrighty. Okay, as a motivation, why is this even an interesting topic? And I want to just grab a couple of diagrams from the literature to motivate why this may be of interest, also to a crowd that isn't necessarily addressing dynamical core issues. So here's a publication by S.J. Lin, who's the main developer of the finite volume dicore and also this is called FE, and the FE3 dynamical core, which is the cubed sphere version of this. Again, this is kind of what we have in CESM, also what NOAA entertains. And this is from a really older publication back 20 years ago, where he's comparing an idealized test case. And maybe, I'm not certain you have heard about this, it's called Held-Suarez test. What it is, it's a dry dynamical core, which is forced by Rayleigh friction and some thermal relaxation. That's enough to know. But it's basically mimicking planet Earth quite well, but it's no moisture, no topography. So we are just running the dry dynamical core with a little bit of forcing that mimics planet Earth. And then when you have those simulations, you can basically assess climate. Climate means just average conditions. So here you see actually a difference plot. Let me kind of guide you through it. This is now the time mean, zonal mean, like time mean 2-year mean or so of the temperature. Of 2 runs, and one is with the monotonicity constraint, or they're both with monotonicity constraints. These are diffusion options. One is less diffusive, and then we have the less diffusive minus the more diffusive. And the only change we have is diffusion in the dicore. And these are now the temperature changes in a climatological mean between the less diffusive and the more diffusive. And I think it's striking to see that we are up to like 1 Kelvin in some areas of temperature difference systematically. So we also see systematic, these are negative temperature deviations. Here we have positive ones, but it's up there. It's not minor, 1 Kelvin.
Why is anti-symmetric? Why it's not symmetric?
That's the question is, why is this an anti-symmetric pattern? That's probably a good, I would need to see how many days he actually averaged. So it may be not long enough to be fully symmetric. You're right. It should have been a fully symmetric pattern because there's no asymmetric forcing. That's a good point. Okay, so let's keep that in mind. This is just due to a diffusion choice, implicit diffusion. I think I also want to show you some other examples. Again, this is coming from the literature. This is now for FE3, the finite volume dynamical core on the cubed sphere. And here we are seeing 2 publications here from GFDL. And let's kind of pay attention, maybe here for the middle row first. Up here we are let's kind of get some orientation. We are counting here the number of tropical cyclones. This is again climatology. And in dashed, where's my mouse? There it is. Okay, I should move. Oh, here it is. There's also down here the number of hurricanes, the stronger category of the tropical cyclones. So here we are seeing a count, annual count, and this is now dependent on the cumulus parameters, so you can think of that as entrainment. How much mixing is there? This is in physics. Yeah? So that is actually, here you see this parameter, it's called E0. So if we crank it up, we are seeing this deviation or variation of just the number of tropical cyclones, pretty striking. This is, again, a physical mechanism, but you kind of get almost the same answer, not quite identical, but if you crank up divergence damping, and that is now something in the die-core. And I want to just mention that this is, 60 goes up to like 110, so it's almost a factor of 2. Yeah? So we are cranking up the number of tropical cyclones not by any physical mechanism, like entrainment, but by just a diffusion choice. And that's here the diffusion or the parameter in front of divergence damping. Gretchen, yeah?
Yeah, so in these simulations, probably you'll show results like this,
Yep.
but how would this compare if you put in noise? Like if you also recognize that we can get nonlinear responses due to just random noise
Yep.
as well. So can you give the magnitude?
Yeah, that is actually a good question because they're not showing that. Oh yeah, so how does this compare, how does this increase in the nominal tropical cyclone compare to what you would expect from an ensemble simulation where you have maybe just initial noise in the initial condition like an ensemble? The authors don't go into that. They don't show ensembles, but I would expect maybe a scatter, I don't know, 10%, 15% or so, not a factor of 2, I guess. That would be my guess, but that's a little bit my take on that, yeah. This is also true for the strong cyclones. You see this kind of trend here, just by cranking up divergence damping. The other thing, and this is also a GFDL publication, this is for one tropical cyclone, this is Hurricane Irma. This is the maximum velocity. This is kind of near the ground, I would say, the Vmax. And this is here the minimum surface pressure. And the difference here in the lines, or with the color-coded, when you kind of see it, in black observations, in yellow monotonic simulations. Monotonic means pretty diffusive, typically, and PD is positive definite, and that's less diffusive. So again, we are seeing this clear signal just by choice of now numerical diffusion, not explicit diffusion, that we are varying the strength of this hurricane really dramatically in comparison to that rather diffusive monotonic as is also true here for the pressure. Yeah, George.
Sorry to keep interrupting you. You haven't said anything yet about resolution. And it's my impression and experience that these changes in numerical algorithms most affect simulations of things that are poorly resolved on the grid. But if you have a well-resolved feature, it's not really sensitive to the states. So
yeah.
Is that the case here? Or?
Yeah, I would need to double check. This is using the Shields model from GFDL, so this is probably at least 10, 20 kilometer resolution, not perfect, of course. That's my recollection for tropical cyclones, but at least it's somewhat decent for global models. Yeah, so that was a good point. But I think what we are seeing is that as you see here, especially with the yellow curve, we crank up diffusion. What we are doing, we are technically decreasing the effective resolution. Yeah? So you basically go with these kind of more diffusive runs to often a broader cyclone, kind of not really resolving details because you're smearing them out with the diffusion. That's a typical case. All right, and last but not least, and then I really dive into my own results. I thought I'd put up here one more picture from MPAS, yeah, because this is more like an MPAS crowd. And this is now a publication from Bill Skamarok, where he is using a baroclinic wave test case. So this is a little bit more idealized. And what really we should highlight here, he is experimenting with the choice of the explicit hyperdiffusion coefficient. Yeah, this is a fourth order hyperdiffusion. And here are kind of the magnitudes. And as we are decreasing here in light blue, we are seeing this is now the maximum velocity, horizontal velocity, wind speed. So as we are using less diffusive, he's shooting actually very much the baroclinic wave maximum velocity is shooting up. This is over the number of days. This is not the default here in blue. I think the default, I think he mentioned, is it's more like the black reference, yeah, the black line. That would be a default choice at the time of this paper, which is a deep atmosphere configuration of MPAS. All right. Okay, so I already spent a couple of minutes here on just the motivation. Let me just show you some real case scenarios from all other dynamical, not all, but many other dynamical cores that's out there. And you can ask many questions. For example, what's the impact? And if you focus on FV3, what's the impact of FV3's numerical design on the fluid flow? This is really what we are hitting home today. And we are just looking at implicit numerical diffusion. This would be the advection scheme and the explicit horizontal divergence damping. And my toolbox is actually, I put it down here, and I also have a diagram, are these more idealized test cases. It's often way easier to see causes and effects in more idealized configurations. If you put the physics in, full complexity physics, you have sometimes a hard time to distinguish, as I claimed, between a physics tuning and like a dicore diffusion setting. For example, we can use baroclinic waves, aquaplanet, or I call it the acid test. This is actually a still atmosphere with a mountain, and nothing should have happened, actually. This would be a perfectly stable, steady state, but of course models are not that gentle. And in that acid test, we see actually the pure errors popping up very quickly. All right. Here's kind of the hierarchy, and this also is a reminder that I'm often using the CSM examples. CSM offers what's called simpler models. This is basically a hierarchy of model configurations, and this is here my diagram, how I view it. So here, for example, would be up here in the pyramid, just dry dynamical core test cases without any physics. You can do it moist, and this is really where I spend probably most of my time. You can also, when you go down the hierarchy, you can do deterministic 10-day or climate simulations with, for example, Hertz-Rares, here the dry dicore. Or you can have super simple physics, like large-scale condensation or so, or Kessler physics. Also in the climate mode, then there are cases where we are calling it radiative convective equilibrium or aquaplanet. Yeah, these are really, and then we go to kind of real cases, like AMIP, atmosphere models with forcing, or coupled Earth system models. Yeah, so I'm mostly playing, I guess, here up in this arena. And I even spent a lot of time, as Andreas mentioned, developing test cases. I have attempted, but maybe I skipped that with this sake of time, to kind of reveal kind of the hierarchy of complexities of test cases a little bit. If I'm just spending 30 seconds, you can make or choices like maybe you want irrotational configurations, gravity waves, maybe you want really just basic flows. What I mean here by this kind of diagram, which is really convoluted, you can have a full Earth, a small Earth, you can have rain or adiabatic choices, you can have a flat Earth, you can have orography. These are all decision points you make when you design a test case. But in respect to time, let me not really focus on that. All right. Okay, here's the lineup of model configurations that I touch upon. And it's FE3. It's also the Spectral Element Dynamical Core, which is in CSM. This is coming from DOE, but it's now a default also at NCAR. We have an older version, the FV Dynamical Core on the Lat-Long grid. We have the MPAS, or MPAS in CSM or standalone. We have a spectral transform Eulerian model. Actually, this is in CSM. And then we have WRF and CM1. And there's a standalone GFDL version from the FV3 called Solo. Let's see whether we get there. And I'm focusing mostly on a test case that is rather new. We just have it in review. If you are interested, you can see some details. But what it really is, it's a baroclinic wave test case with mountain. And you see the mountains here. And what inspired us, let me kind of highlight this. These long mountain ridges look like maybe the Rocky Mountains or the Andes. So this is kind of what we were choosing in terms of our mountain shape. And this is also maybe good news, well resolved even at 1 degree. Yeah, so we wanted a test case that's not requiring convection resolving scales. Here's the initial setup. Moisture is also temperature, the U velocity, and surface pressure. This is rather balanced. And here is, when I kind of just play this is how the test case looks. So we have the mountains down here in contour, the sea level pressure. We see some precipitation developing after a couple of days. So this is now in hours. We have a temperature evolution at 850 with kind of typical horizontal, or temperature fronts. Here's the water vapor. And this is kind of just a 10-day simulation. So this is really how the test case goes. Yeah. So it's a baroclinic wave. We see low and high pressure systems. The other thing that we can pay attention to, and let me play that. This is an example here from the Spectral Element die-core, that we might also see these weirdos, yeah, these more strange-looking effects. I come back to that if there's enough time. This is actually a very different animal than a baroclinic wave, what we are seeing here. It's more like acoustic gravity wave modes revealed by this test case. Okay, let me just go to my next slide. Let's see. Okay, all right. I start with the implicit numerical diffusion, and that's really a harder concept, which I really can't dive into, but let me just give you the main message. What this means, it's determining the diffusivity of that operator. This is basically the advection. This is now in conservation form, like a conservation law here for the potential vorticity, or potential temperature, sorry, here multiplied by some density-like quantity. But this is really where numerical diffusion can act. This is basically providing, let's call them limiters, monotonicity constraints, positive definite constraints. So that's really all you should know. Yeah. So it's a complicated mechanism how to basically, discretize this term. And FE3 offers many, many options. You see some numbers here. We are not focusing too much here on the meaning. Let me just point out 5 would be the least diffusive, and all the others are more diffusive, especially number 6. And these are popular choices in GFDL's model configuration. You can even have different choices for different terms. So if you transport kinetic energy or vorticity or potential temperature, you can even make other choices, which is unhealthy, not recommended, but this is a possibility already. Okay, and here is just maybe a heads-up look. Now you see some of these choices. This is the least diffusive one, the more diffusive one, and these are also more diffusive. But you see, for example, in some you see grid imprinting from the cubed sphere. Here you see actually a really developing cubed sphere wave already in this more diffusive one. This is now becoming really noisy, actually, and develops into its own life. This is a better simulation. I'm showing actually the vertical velocity at 850, and you wonder why the color looks so strange. I'm saturating the color on purpose to highlight the noise. Yeah, so this is you see this is now starting all over to see kind of initial kind of wave activity, but really where you see the most impact from diffusion is really in the grid imprinting signatures from the cubed sphere, which has like 4 special points. And also we see this here developing, which is really initiating circulation, not healthy. Yeah? And the only thing I change is the diffusion in the numerical scheme. Okay, if we do just a close look at that, again, we have these choices here, 5, 6, 8, and 10. Well, this is now just at day 5, a snapshot. They kind of look alike, yeah? So maybe at first sight, you say there isn't really too much of a difference. You do see differences right away if you just pay attention to the minimum, yeah? And this would now just highlight the minimum the minimum pressure. And you see it even better here, where is a timeline in days of the minimum surface pressure. And here you see in 5 would be here the red one. And let me highlight that this is not just a small difference. Yeah? We are over 5 days, we have 10 hectopascal difference in the minimum surface pressure. So this is a kind of more major change even in the circulation. Although the patterns, they kind of still look alike, yes. But this is kind of already pointing to the essence of this. You can also ask the question, I'll show you FE3, and now you ask the question, how is FE3 compared to MPAS or to SE? Let's kind of take a look. So here we have now a comparison of the spectral element, final volume, FE3 and MPAS. So MPAS down here, standalone. And these are now, these are snapshots at day 5 of the minimum surface pressure, not minimum surface pressure, but here's a timeline of the minimum surface pressure. And we are seeing actually 3 models on top of each other, which is MPAS, the spectral element dynamical core, and FE3 at the least diffusive setting. But as I'm switching in black to the slightly more diffusive setting, I'm jumping big time. And this is kind of an indication, okay, we don't have an analytic solution, no, but if 3 models agree, maybe there's an indication that this could be a reference solution, yeah? So let's kind of maybe assume that this is the better solution without really technical proof, yeah, because of no reference. But this is a big jump just by 1 parameter change. And this is even just, well, you can go a little further, and then I kind of jump into the divergence damping. You can even go a little further. You know, what happens if you change resolution? So like 100-kilometer spacing or 50-kilometer spacing with these more diffusive or less diffusive options. Again, that's easier to see when you go after a timeline. Here, a couple of days. This is minimum sea level pressure. And the interesting part, and really the take-home message is, as you kind of observe in red and here in orange, the least diffusive options, you kind of have this overlay of red and black. And what it really means, the least diffusive coarse resolution is showing identical results than the high resolution diffusive one. So we basically, all the bang for the buck you pay when you go to high resolution is lost due to the diffusion setting in this, and this is also reflected in the accumulated precipitation. So it's not actually just in the dye-core, it now impacts, you know, the precipitation regime. And this is also true, the least diffusive one is in orange, so we have actually the most precipitation in that, and then here in red and black we overlay, but basically we have two different horizontal resolutions in these. All right. It's also very clear to see the effects of diffusion in these are kinetic energy spectra. So this is kind of the spherical wave number regime, and here's the amount of kinetic energy at, this is now an aqua planet at 200 hectopascal. You see very clearly the loss of energy in this more diffusive red option when you go to a more diffusive configuration. And we are not talking about the tail, we are talking about energy lost at wave number 20. Yeah? And you think wave number 20, okay, this is a 1 degree resolution, like 100 kilometers, but you think wave number 20, you should have a good grasp on. No, not with a pretty diffusive configuration. Okay. This is mimicking, and this is now from GFDL, so what I see in Aqua Planet in terms of behavior in the kinetic energy is mimicking exactly what GFDL will tell you about their own models, and this is now at very high resolution. So here we are seeing 13-kilometer shield model. This is a GFDL version. Here we even see a 3-kilometer shield configuration, and again, we are looking at kinetic energy configurations over wavelength. Really, where you only need to pay attention to is like shallow, let's see, black and blue. You see clearly blue has more energy. Yeah? So this is at the 3-kilometer. Black is kind of here in the mix, losing energy, not maybe at wave number 20 in this case, but also somewhat early. And here we see the same kind of behavior. Where's my mouse again? Let's see. Oh, here it is. Here with H-Orts, again, more diffusive in green, kind of see this clear tailing off. One consequence, and let me watch the time a little bit, one consequence is that diffusion is also, and again, this is more diffusive, increasing peak precipitation, alrighty. So now we have precipitation in the tropics, not the mean is rather similar, but in the tropics we have a different distribution now of precipitation due to the diffusion choice. And this is also reflected in many other statistics. Maybe let me skip over that with respect to time. All right, okay. Switch gears a little bit. Okay, I talked about implicit diffusion. Let's go after explicit. Yeah, something I slash on, I add to the model after the facts. And I bet most of you have not seen this, so I thought I'd sneak in one equation, how this is done. So here you see actually kind of the mechanism. And the Q's here will denote the order of that diffusion. So you can go second order, fourth order, sixth order, eighth order in this model. What it really does, and here's kind of the analog. Here you have, let's assume this is a horizontal momentum equation. Then you apply like a divergent operator to that. Here you see the divergence damping, so it's a coefficient times the horizontal divergence. If you do that, you see now we are developing a Laplacian in front of that diffusion, and that's really why we call it divergence damping. So it is Laplacian diffusion of divergence here, second order, but you can do higher order if you want, yeah? As denoted here. Okay, let's just focus maybe on the box here. So we are looking here at 6th order divergence damping versus 8th order divergence damping. well, common sense will tell you higher order is better, typically, because higher order is more scale selective, so you're less aggressive, typically for the resolved scales, but that's not necessarily the case. You see a little bit of trouble already here in this higher order configuration. You even now see noise developing into a circulation down here, and kind of already points to a point of almost instability, actually. And that's here the issue. Yeah, you think higher order is better, but it means you can also under-diffuse, yeah? So it's maybe not enough diffusion, and this diffusion is indeed needed to keep this model from blowing up. But here you see clearly it's starting all over, that it's not necessarily the answer. It's not always higher order is better, yeah? Let's kind of take a look. So we have here second order divergence damping, fourth, sixth, and eighth. Again, this is higher order, identical coefficients in front. And this is again the minimum, not the minimum, the surface pressure. Here's the minimum sea level pressure over some time. And here probably the best ones are overlaying. And this is actually the fourth order and the sixth order. The second order, yes, more diffusive, is giving us, not as deeply evolved sea surface pressure minima, but also this overlays with eighth order. And there is already a hint that we are looking strange here in this, you kind of see the noise already popping up, actually. So under diffuse, basically the conclusion here is that you are even in this under diffused regime. And what I mean by that, under diffused is close to instability. Yeah, so this is, for example, an example where it's not blowing up yet, yeah, but here's an example of a baroclinic wave simulation, a vertical cross-section of V, the meridional velocity. And if you see that, you don't want to be in that regime. And there are two differences, but the real difference is that's eighth order and that's sixth order divergence damping, yeah? And the sixth order is controlling this noise quite well, but not eighth order. You also see this in, again, kinetic energy spectra and let's kind of get some orientation here. This is in blue, the most diffusive, then we go to green, less diffusive, then we go even less diffusive, and then we go to these guys. You see they have an upward hook. Where's my mouse? Oh, here it is. They have an upward hook. That's very, very unhealthy. If you see that in your kinetic energy spectra, you are kind of blowing up shortly. Yeah? So this is not good. Typically you want kind of a flat tail. Yeah? So kind of going down. This would be pretty okay here with sixth order divergence damping. And also with respect to time, let me skip over some of the aquaplanet studies here. Okay. I have 10 minutes or so. I want to wrap up with a few other thoughts, and not just FE3, because I thought, it's actually broader than that. Yeah. So the one thing that I had denoted really early on is a little bit of a strange thing in the spectral element dynamical core. Here you see it. That what I call the spectral, this is actually a configuration of a spectral element, FE, FE3, MPAS. And we again looking at the vertical updrafts at 850. Oh, God. Ignore. And we are seeing this wave, pretty persistent. We are day 8 here. And not going away, but going away in other decors. So a little strange, I thought, when we first saw that. So we were digging in a little bit. And there's also a question, can you, when you go from 100 kilometer to 50 kilometer in this baroclinic wave, can you change the character of this wave, and what is it? Yeah. Well, the answer is, you can't really change it. Well, it's still there. It's this wave, and it's not improving. We thought the trigger of this initial wave is actually the mountain. The two mountains are a little bit unbalanced in the initial condition, and they trigger this wave. It's super high speed, and that's really what we wanted to see. How high speed is that? And before I do that, we also convince ourselves as we are going, for example, in the dry case from like 150, 25, 12 kilometers, it's really not going away. It's even actually increasing in magnitude. So that was a little bit unexpected. We see two things. We see actually they shrink in size, these waves shrink in size, but they increase in magnitude. So they're not going away though, which we were hoping because with higher resolution you get a better initial state. Okay, let's kind of dig in a little bit. Also, we see, not focusing on that, some noise developing which is a very different issue. All right, we thought we can mimic that in a really idealized configuration, even more idealized than baroclinic waves. And what I mean by that is this acid test. What it is, and here's kind of the recipe. A dry atmosphere, doesn't rotate, isothermal, state at rest, no wind. It has an analytic solution, which is nothing. Yeah? And then we put in a mountain. And that mountain is good enough to perturb. Yeah? So what we are seeing is now, these are now, again, updrafts at 850. We are seeing the magnitudes. This is now kind of a loop here over a couple of days. We are seeing a super high-speed wave now kind of propagating in the horizontal direction. And it is so quick that you can, when you kind of look, and this is kind of our next step, it can be really identified as an acoustic wave. This is a lamp wave, horizontally propagating, even possible in hydrostatic models. Okay, and it's not just a dream. Yeah, we have these guys actually in the atmosphere. This is now from Hunga Tonga, yeah, the volcanic eruption that produced such a wave. Yeah, this was kind of a lamp wave that originated from the eruption. Here you see it, and going really with the sound speed around the world, very similar to actually what we have here in the spectral element dicore. Okay, yeah, you can track the wavefront, in various directions, and this is what we did here. So this is now a Hofmüller diagram, the time, and kind of here at the equator, and here's longitude. This is a test. I wanted really to know, is this an acoustic wave? If yes, it should be sensitive to temperature, to our initial choice of temperature. So let's say we have a cold 270, a warm 305, and a really hot 350 initial condition. And yes, you do see a little bit here indicated by where the errors. You kind of see the frontal zones, I guess, of that wave as it propagates in the zonal direction. This is indeed the quickest, and it kind of so this is slowest. So this takes more time, basically, yeah, to reach the edge. This is medium, and this is the quickest. And we can really nicely compare this with, theoretical sound wave studies, if you want. This is a linear 1D sound wave, the dispersion relation. And if you just compare the predicted sound wave to the actual measured, estimated speed, it's actually a pretty okay match. As you go to the higher temperatures, we increase in sound wave speed, and that's exactly what this wave does. Okay. Okay, I spend maybe a few more minutes, and then I wrap up. Yeah, you can use the acid test for many more studies. For example, here you kind of see the acid test a little bit in motion. Yeah, here we have the mountain, and this is now just let it go, basically day 4. If you think there should be nothing, so analytic solution, every color that pops up is an error. And you can compare dicores again here, FV, FV3, Eulerian. What really surprised us, though, was, again, the impact of diffusion here on the Eulerian dicore. Very unexpected. So with the default diffusion, this is hyperdiffusion, 4th order, and a little bit of sponge layer diffusion up here. We see pretty big, this is now the zonal wind, the zonal wind error after 4 days of like 0.5 meters per second. If you have no diffusion, you bring it down to almost nothing. Yeah? So the only thing that's different is diffusion. That's also visible here in the vertical velocity, just kind of highlight the magnitudes a little bit. We can also, and now let's take a look at, this is the 2 other models here. We have, FE3 and SE. This was also very much unexpected. So we have a huge error, now 1.2 meters per second here, actually error here in the spectral element model. That was, it's even more in the default configuration, 1.5. And again, we are just experimenting a little bit with diffusion settings, so I put down a couple of the nameless parameters, but it's not going down that much. So SE actually is pretty horrible at keeping this initial state stable. So that's you think it's actually what we think pretty accurate model, keeping the lamp wave around, but not in this measure. All right. Okay, let me skip. I wrap up with one more very short thought on, how how diffusion also acts at convection resolving scale, which is probably of most interest for this group. Lou Wicker is investigating a lot of also idealized score line experiments and using WRF, CM1, and FE3 solo. This is a GFDL configuration. And he uses score line tests for different shear configurations. Here you kind of see wind shear configurations. And let's just focus maybe on the 6-meter wind shear. You kind of just see the outline. What he has been seeing that, and this is now also true for Rufus or the UFS, the Unified Forecast Model at NOAA, we see extreme rainfall in the FE3. We also see extreme updraft speeds. And the question was, is this indeed related to diffusion? And the answer is yes. Here you see just a couple of we call them cloud objects. So at hour 1, we see this is where the black lines appear. We see some squall line seeds, and then here in the later hours for the different models here, FE3, WRF, and CM1, you see different cloud objects. Let's maybe not dive into this definition of cloud objects, but what it really, this is what it's boiling down to, what we're really seeing, this is now average updraft speeds over, this is a vertical cross-section here is W, and FE3 is kind of almost off the charts a little bit. And this is now after 1 hour of simulation. It gets a little better after a little bit more time. But we are comparing this here to WRF CM1 as kind of MPAS should be in the picture as well in the future, the limited area version. I bet MPAS will be close to these two models. So this is kind of off the chart. And what Lou also could show, and this is now my last kind of point, he showed by again, modifying divergence damping coefficients. Here the 4th order, or it's actually 8th order, diffusion coefficient by halving it or have a quarter. He's bringing down the updraft speeds kind of drastically. This is not so true in some more shear, so if you have more shear, it's a little different, but in this weak shear leaf, in the weakly forced configuration, this is what we're seeing. All right. Okay, let me close. Okay, I basically, revealed a couple of the complexities that are hidden in the dynamical cores. Some things are also unexpected. Some are counterintuitive. For example, in the acid test, FE3, as you go to final resolution, increases its error. It's a little bit strange. What normally you think increasing resolution reduces error. We focused here on hydrostatic scales and idealized test cases, but they do tell us a story about the real world. Very complex, and I'm often citing an analogy, is coming kind of from estrogen. So there's a lot of medicine, and some medicine is indeed needed to keep our patient kind of healthy. But some medicine, and this is true for FE3. For some medicine, like 8th order divergent damping, the patient is barely alive, and then you need other medicine to battle the side effects of that medicine. So it's really a complicated story. I think it's worth looking at or asking at least when you have a model at your hand. And often, and this is my last word, there's a gray zone. Diffusion could look like physics. All right. There is here a list of references if you want to go back, but let me kind of stop here. Thank you.
Thank you, Christiane. Since we had a couple of questions from the room already, we can take one from online. Exciting work from Joseph Chan. Dumb question for a non-dicore person. Could you comment on the viability of using high-resolution model to determine the best diffusion choice for a low-resolution model? I'm guessing artifacts from diffusion schemes weaken with small grid spacing.
Yeah, that's a good point, and maybe not an easy answer. Some things you can't tune. So numerical diffusion, for example, is just inherent. It does vary with resolution. Also, well, if you have explicit diffusion, you actually need to tone down your diffusion coefficient. You can't use, it's hard to say if you have a really good high resolution configuration with that diffusion coefficient, you could not grab that diffusion coefficient applied to coarse resolution. That's unstable. So it's not an easy answer, I would say. You can get an idea what a reference solution might be at high resolution. That's kind of what we are doing also with different dicores, the high resolution. But it's not just a transfer of information from a high-resolution regime. Often kinetic energy spectra probably a good bet to see the effects of the tail and or the slopes that you might get.
Questions from the room? Ah.
So why does the FE3 have this rich assortment of
Excellent
diffusion
question.
schemes and other models do
It's
not?
engineered. It's engineered. They saw a need. I can't 100% answer that question. And I think more and more things were added to the diffusion portfolio. For example, vorticity damping, which I didn't really dive into, was added years after the initial configuration because it was seen that the implicit diffusion is not, in some cases, and that was dependent on resolution, is not operating enough or not giving enough diffusion to vorticity motions. Divergence damping was always needed because divergent motion were never diffused actually internally. This has to do with some choices of the design, like a D-grid is inherent here, which has some numerical artifacts built in. If you basically, without that, you can't run it. But horizontal diffusion, numerical diffusion did act on vorticity. The 2 delta Z also didn't talk about sponge layer diffusion in the vertical was added later because they saw instabilities in the stratosphere mostly and wanted to just Richardson number dependent mix things. It was just engineered. There's no physical motivation for most of these choices. And it's a very complicated portfolio. They will tell you for all resolutions, for all scenarios, for all configurations, you will need to tailor this, which is very uncomfortable actually as a model user.
So that was a really nice talk, number one. Number two, another non-expert question.
Yeah.
Are there similar sensitivities maybe to the time step you use in the model?
Oh, yeah, excellent point. I could have added slides like that. This is a whole talk by itself. Yes, there are, especially in FE3. It depends a little bit now on the model. I had glossed over one with SE, the spectral element model, over an area of noise. That was a time step dependent noise issue. It depends on the physics dynamics coupling. And time step is actually, maybe for those who are not familiar with time steps, it's a complicated topic because we have time steps in the dicore, even sub-stepping for diffusion. We have a physics time step. So a time step doesn't mean anything. We need to now dive down what time step. And often it's a physics dynamics coupling time step that is a problem. Yeah, so the interval, very sensitive results are sensitive to that in the real world if you have a 15-minute or half an hour coupling frequency, for example. Very good question. Yes, absolutely. There's Kevin Weiner at NOAA who's doing a whole study of time step sensitivity in the UFS right now.
One other non-expert comment. It makes a non-modeler kind of skeptical of all this.
100%. And I think
just
we
to
should
be aware of it is a good thing, right?
100%. 100%. Yes, that's really what I want to shout out here. It is not just a given, yes, even in CMIP models, those effects exist, and then of course typically we tune the physics, but that's maybe not the only thing we should be concerned about, Sure, physics, yes, there's many things to maybe in tuning, that's an art by itself. You look at top of the atmosphere, radiation balance. Often it's moisture related, of course, yes, but it's also the dicore because the dicore acts, and I glossed over this in some of the aquaplanet studies, the diffusion in the dicore acts as a transport mechanism for moisture into the Arctic. Nothing to do with actual transport, is diffusion transport. So you get more clouds in the Arctic with more diffusive configurations.
This question may be more appropriate for Lou Wicker, but since you showed some of his results, I'll ask you anyway. The last time I talked to Lou in person, he was exploring the possibility of those differences you showed in updraft strength were also, obviously the numerics are playing a role there, and the diffusion in particular, but he was also exploring the option, or the explanation that some results were due to the different governing equations in the model. And some people think, governing equations of fluid flow, we know what those are. Well, it's actually not. That's true. I think that's true statement for the dry atmosphere, but not for the moist atmosphere. So do you know what the status of that explanation for some of those differences?
I don't think I heard anything new from Lou about that. But even in the dry dicore, let me say it this way, you make a choice whether you, for example, transport temperature or potential temperature. It's not even true, the equation, how we are phrasing them, is not even unique in dry dynamical cores. And once moisture is in the mix, it's becoming even more complicated figure. We can also make choices. For example, we have the advection form or the conservative form of advection. That's a choice, and all will play a role in your diffusion characteristics.
Yeah, well, that's getting into the issue of numerical methods too. But I say, just give me a sheet of paper and write down the equation for your model, and different people will write different equations for moist atmospheres. So,
yes.
That's even before you start discretizing and choosing numerical techniques and whatnot.
True, and it even comes down to things you might not even think about. We think of physical constants like Cp as a constant. Not true, yeah. Technically, it's temperature dependent and moisture dependent. Do we do that? Maybe at times. Actually, CSM has this weird mix. Yeah, it does not do that. So in the spectral element dicore, we do a moisture dependent CP, but not in the dicore, but not in the physics. Yeah, so we even have inconsistencies in one modeling framework how we are dealing with coefficients or physical constants. This is all basically under the rug. Yeah, so that's what really my point is. It makes big differences. Peter Lauritsen can tell you in the energy budgets. Actually, even these choices of the constants. Yeah.
Any other questions? Do we have?
Online that I accidentally got rid of. Let me restore it.
Oh. Jean Brasseur, given that numerical diffusion is non-physical, would you agree that as a general statement, one should aim to minimize added diffusion to just enough to suppress numerical instabilities?
Yeah, I think that would be my approach. Yes, you want to just that medicine should be just enough. Yes, but you don't want, and it can be not enough. Yeah, and then you have the other diffusion that battles it. Yeah, it should be sensible, just enough for sensible tails in the kinetic energy spectrum, and also no noise in fields. But you should not do more. Yes, I agree with that.
There are.
It's not a question, a comment. Do things like that may driven climate change skeptics to say, you guys don't know what you're doing? Are you sometimes attacked by...
Yeah, that could say that. I think they could. They could also talk about that, though, for the convection parameterization or any other physics scheme. Yes, it definitely could be a topic that people could pick up, yes. Yeah, but I think as scientists, we want to know about it. I think it's still good to reveal, especially in this community, what we are dealing with, and to do a better job as good as we can. Yeah.
Okay, if there are no further questions, let's thank Christiane again, and don't remember there's coffee and cookies outside. So please join us for an after seminar get together.